the first talk today will be given by, it's our great pleasure to have Omer Gurdogan, who will tell us about cluster bootstrap positive geometry and astrology for octagons. Please.
Right. Thank you for the introduction, and also thank you for the all organizers for putting together this great meeting workshop, despite all the adversities and making us able to talk to each other despite we can't meet. So it's been so much fun and interesting workshop. So judging from the audience last week, i.e. physicists and mathematicians, I thought it would be a good idea to give an overview of what people who do cluster bootstrap do. What the methods are, what the philosophy is, and what they expect from positive geometries to strengthen their game. And I'm not sure how many of these mathematicians are right now in the audience, and physicists probably who are familiar with cluster bootstrap might want to make a coffee or check emails for a few slides for during the introduction. So let me warn you, a lot of the stuff will be very familiar to most of you in the beginning, especially from previous talks by Yorgos and Mark as well. And then I would like to make some speculations in a slide or two about the newly observed phenomena in the new for mass kinematics that the octagons have as well. Right. So let's start with the roadmap, because I have to take a linear trajectory of the talk, order of subjects. They're all revolve around the cluster bootstrap idea. For that, I will just mention, review the ideas of the symbols and the alphabets and how they relate to positive geometries. So, and then I'll introduce the concept of adjacency of these symbol letters, alphabets, and talk about various polytopes that these adjacency rules might come from. They're all conjectural at the moment, so we have many candidates to infer adjacency rules from, which I will also elaborate on. And then I'll do a detour into Young invariants and leading and Landau singularities and their adjacency properties. I'll talk about this story a bit, and then I'll go into the octagons and tell you some things about that. Okay, so that's the plan, but everything is going around this bootstrap idea. And what do we do? Well, we do what quantum field theory doesn't tell us to do. What it tells us to sum over all intermediate states. That's what quantum theory says. And the intermediate states, how do you compute them? You write your Feynman diagrams, or you compute integrals using the loop amplitude or any other method. So you list all your intermediate states, and you need to average over them. So i.e. integrate these integrands, and this is hard. And when you're lucky, you compute the scattering amplitude. But what you sometimes can do is to just write down the only possible answer. And to do that, you need a lot of information from positive geometries, cluster algebras, these things. Right. So this is a general idea, and there are many achievements of this idea. What are the achievements? You can compute many amplitudes that are impossible to compute by writing down integrals and integrating them. For 6 points, MHV amplitudes have been computed up to 7 loops, and an MHV up to 7 loops, even though I think this is not available public, right? But hopefully soon. 7 particles up to 4 loops, both NMHV and NMHV amplitudes have been computed by trying to write down the answer without seeing a Feynman integral. And there are other quantities that you can bootstrap. Before I go to right pane, for example, today there was a paper by Song. You can compute Feynman integrals by bootstrap, or like we've done a few years ago for 7 particle integrals, or many other people have done. You can bootstrap if you know some information about these results, you can write down the answer. For example, form factors of they're like scattering amplitudes. It's like an operator with a state, two scalars and a gluon, for example. And recently they had been computed up to 5 loops by Lance, Andrew, and Matthias. And now this is available, this is computed up to 8 loops using the bootstrap technique. So 3 loops at a time. I think Song computed 3 loops at a time in their paper collaborators. So if you're not computing 3 loops at a time, you might be trying to compute Feynman integrals. And bootstrap is when applicable, it's a very promising approach to scattering amplitudes. That's the message to people who are not familiar with this strategy. So best way of computing Feynman integrals is to compute none, is the motto of my interpretation. Okay. And what do we compute? We compute a quantity, a finite quantity, instead of the scattering amplitude, which has UV, which is divergences in general. If you can define a finite quantity, what we call E, the remainder function, which will be the only thing that you need to compute because its relation to the scattering amplitude is well defined. Yeah, that's the thing you bootstrap. And in the cases that I'm talking about, it's given in terms of polylogarithms. And so what are they? If you compute a differential of one, you get a d log times of another function of that class. But you will get that if you iterate a differential. You take this coefficient, you compute a d of them, and you get another d log. And then you record here as an index which coefficient of which d log you then took and then computed d of. And the iteration of that, so recording what d logs you get and iterated these, gives you the symbol of the remainder function. And the symbol is enough to nail down the remainder up to constants, and it is at the moment a technical issue to reconstruct the multiplicity values. So I will loosely speak about the symbol of the remainder and the remainder as the same object. And the arguments of the d logs is the alphabet. So these are functions of kinematics, typically rational functions, but also non-rational functions of the kinematical invariants of our Plücker coordinates encoding these. Okay, so this is the object. This is the object we're reconstructing. It looks like this. And more in detail, for MHV amplitudes, it's just a Q-linear combination of words of length 2L. So there's 2L symbol letters concatenated next to each other, put next to each other. And for non-MHV amplitudes, it's slightly more involved. You have the Q-linear combination of these words multiplied by some Yangian invariants. And for simplest non-MHV case, it's the next to MHV case. And here you have the symbols multiplied by R invariants, which are object with 5 Plücker poles, 5 labels, each pole for one deleted label. And these can be computed as volume functions in positive geometries, or I don't know. Okay, so these are the objects I'm talking about. And bootstrap philosophy boils down to replacing reinterpreting the problem of computing scattering amplitudes with stringing letters together into words and trying to find the correct words. For that, the ingredient you need is an alphabet. So what words am I playing with? And for n equals 6 and 7 particles, these are given by cluster variables of GR and 4, n cluster algebras. Then you would like to know which letter appears where, because I will take all words, but that's too big a space. So that's one thing you need to know. And then to constrain what words you can write, you would like to know what appears next to what. That's one other thing. Or then you would want to know how to construct longer words. So we'll ask like what triples can appear, what quadruples can appear. So these are the natural questions that you ask in this game. And then you would like to find a space, linear space, in which these symbols live that obeys these constraints. So has the correct letters, correct adjacencies, correct multiples. That's this space. But that this space is, I would like to stress that it's not clear because yeah, so we choose our letters, we choose adjacencies, and ideally in that space there's no junk. So every element of the space corresponds to something physical, but that's not something we have as far as I know. So we need to weed out a lot of junk in the spaces that we define with rules that we know, and it's still not a problem to find all the rules that define all the all the symbols that make sense. Okay. That's something I wanted to emphasize here. Right, small print. As you see, it's not small because I'm not trying to sell insurance. I'm trying to be honest. So these are the results that you get from bootstrap strategy are all conjectural results. So you write down what should be the result and you check it and it's there. So there's no like first principles that prescribe you what to do in this game. Like a formulation of quantum field theory, like write down. Feynman said, okay, it's just the diagram, draw diagrams, and the result is what you get. So we're not there yet in this game. And so far, it's restricted to polylogarithmic amplitudes in mostly in maximal supersymmetric animus theory. So we need to expand that, and we need to understand these multiple rules more because the knowledge of the alphabet is far from enough. So in many cases, in other kinematics, we know the alphabet, at least a given loop order, but the symbol spaces are vast, and we need some dynamic information to nail down the symbol of the answer. So the applicability of these methods dies down very quickly unless we have further information that we don't have yet. Okay, so an example, 6-point particles. The alphabet is given from a GR4,6 quantum cluster algebra. Of course, we want homogeneous combinations of its pluckers, so we multiply the torus action. And so this is the initial quiver for this cluster algebra. There's some pluckers, and they're connected to each other by some arrows. And some of them are in blue boxes. That means they are frozen, and they're active ones, 3 of them. So it's a rank 3 algebra. Cluster algebras have been introduced many times, and many of you know, so I'm just reminding for completeness. And you can mutate on these active nodes and generate other quivers. In this graph, each node corresponds to a cluster, and each edge is a mutation. So for example, these 4 clusters along the square edge mutate to each other like that, and in common they have one cluster variable, the plucker 1, 2, 4, 5, and therefore I can also associate a facet of this polytope with a letter. So that's a different way of seeing it. And you see from this geometry what what letters appear where, for example. Initial entries are of the form I minus 1, I minus 1, I, j minus 1, j, like that, these guys. And there are final entries, they're here, 6 of them, pentagons, and there are frozen ones, you don't see that, but never mind that. And you can define x variables too, which we're talking about. These are defined in a cluster for each node, as simply incoming nodes divided by outgoing nodes. Okay, so that's a review of clusters, and we have an alphabet. There's another point of view to these, which appears to be more fundamental for the bootstrap game. So because, well, for the reasons I will mention. So cluster algebras are very intimately related to tropical Grassmannians, positive parts of tropical Grassmannians. And a construction of the positive part of the tropical Grassmannian is due to Spire and Williams. And the recipe goes as follows. You express all the pluckers in terms of the x variables. Sorry, there's a maths and physics convention confusion there, so that would be an x variables of the initial cluster. So basically, we use web diagrams, web matrix, and you evaluate the pluckers of that web matrix. You tropicalize the polynomials you get, and you get piecewise linear functions. And the cones in this are k minus 1 times n minus k minus 1 for the rank of the algebra, cluster algebra. The cones where these polynomials are linear, well, are cones. So the cones are defined like that, where the regions of piecewise linearity. And once you cross a wall, the linearity is broken. So you make a minimum equal, for example, in the tropical polynomial, and you go to another cluster. And crossing these clusters in simplicial cases is exactly, so crossing these cones, walls, is a cluster notation. And these fans also can be thought as the Minkowski sum of the Newton polytopes of these polynomials. So they are very close related objects, but they are only equal in the finite and simplicial cases, like those ones I'm showing right now. So on the left, you see the fan for GR2,5. It has 5 cones, like that. And I intersect it with the unit circle. I get a pentagon, so 1, 2, 3, 4, 5. And each edge of this is a cluster. That has 2 rays that correspond to the cluster variables of this cluster, the G vectors, actually, G vectors. And in 2,6, 3-dimensional rank 3, and each triangle here in this picture is a cluster, corresponds to a cluster. This is a picture that's obtained by the recipe, the spiral recipe I just mentioned. But each cone that I'm highlighting is a cluster. So that the dual of this gives you this Stashev property. Okay, but in general, these fans are not simplicial. And when finite, they are triangulated by the cluster algebra. So you merge clusters together to make these non-simplicial cones, and that seems to be relevant for the bootstrap program. So I'm reviewing this to stress that relevance. Right. Okay. So we talked about what letters are. So what can we put next to each other? We made an observation back in 2017. 2 symbol letters appear next to each other only if there is a cluster containing both of them. For example, the extant Steinman relations can be formulated in this way. So these square faces of the Stashev polytope correspond to these pluckers, so 2, 3, 5, 6, and 2, 1, 2, 4, 5. And they are like 3 particle channels. So blue one is like that. This plucker corresponds to this 3 particle channel. And the red one corresponds to this 3 particle channel. And you see these faces don't share an edge face. These facets don't share a face. These codimension 1 faces, which are letters, don't share a codimension 2 face. In fact, they mutate to each other. So the 2, 3, 5, 6 mutates to 1, 2, 4, 5. And I think it's in this mutation. And they don't appear next to each other. This is the statement of the Steinman relations. But you have other constraints on what can appear next to each other. When you consider integrable words with physical entries, somehow they become equivalent. As far as I know, that's not understood very well either. But you can, no one stops you from considering more general words without physical initial entries. And then they are different statements. So the adjacency relations you get from the cluster polytope are more general than the Steinmans in general cases, in non-physical cases. Okay. Right. In the simplicial cases, where the fan that you compute by tropicalizing polynomials, or the Minkowski sum of the Newton polytopes of some polynomials that you consider, and that's simplicial, then the adjacency statement is translate the two things being in the same cluster translates to there being an edge between the two g vectors corresponding to these a coordinates or x variables. Also makes sense in the non-simplicial cases, but it needs to be more involved. So it's not that so you would say they are in the same cone, non-simplicial cone, but that's not quite right. The statement is that there's an edge between the two. So yeah, so this if you have a non-simplicial situation, we will be looking for edges between letters. And there, given a k and an n, k we fix as four dimensional kinematics. For the 4 components of the twistors, momentum twistors. And for given k and n, a multiplicity, you can construct various fans. For example, you can tropicalize all your Plückers. And that's the construction of spiral envelopes. And but you can also choose the parity invariant subset of those. Like that. So there's 2 types. The I plus 1, JJ plus 1, the distance types, or the I and J bar, J minus 1, JJ plus 1 types. And you union over those, and you get a different fan. Or you can compute the parity completion of the Plückers. So linears and Plückers can map to polynomials of Plückers and tropicalize them, and you get a fan. Or you can, if you have a finite clusteral algebra, you can write down all the cluster variables and then compute the fan you get from them. And this will be the simplicial one. So has to compute that. Yeah. So, and right, why am I going through these? It's still under investigation which guidance of which fan we should take to construct bootstrap amplitudes. So yeah, there are lots of questions to ask there. For example, for 4,7, the raise of each of these versions is 42, and for the 42 letters of this case, but the number of edges different. So the cluster fan has 399 edges between these rays. That means 399 allowed adjacencies, but the parity invariant one has 385 edges. And yeah, so that means some of the adjacencies are disallowed by this one. MHV amplitudes so far, like this fan, so fewer neighbors they require, but we don't have enough data to confidently say which one is for MHV amplitudes, which one is MHV amplitudes. So there's more work for astronomers. So by this astronomy and astrology terminology I took from Mark, I hope you remember his talk last week. Astronomy is the business of looking at the results and looking for patterns. Astrology is trying to explain them by these facts. And he's not here to defend himself, say himself or not say I haven't said that. So his collaborators should feel free to correct me. Okay. So, and, oh, I changed my page on my iPad, but the laptop shows the old page. I don't know which slide you're seeing. Do you see non-simplicity?
Sorry?
I'm having a connection issue, I think.
We see
Still says,
nothing.
still says astronomers.
Okay, so
Astronomers, yeah.
very good. I changed slide and I'm waiting for that to catch up on the other side. Right.
You can also try to unshare and share again, maybe.
I think that's will be the quickest.
Right.
Unshare.
Sorry about that. Oh, Zoom seems to be frozen on my iPad. Okay. I cannot start screen share while the other participant is sharing. Okay, now it seems to be working. Okay.
Yeah.
Are we back? Yes. Yeah. Now.
Yeah.
Okay. Very good. Sorry about that. That
Okay.
no. So one of the things I want to emphasize is triples. When you say triples, you imply pairs, and you can look at the triples implied by pairs to consider all the integrable words that obey the pair conditions. But the triple conditions may allow you to make statements in the octagon cases. So let me therefore spend some time to describe what the triple statements are. So there is an observation that only two kinds of triples appear in integrable words obeying adjacency conditions. Either they're of the ABC type, or as we call them, AXA prime type. So that's a bit of internal terminology, so let me explain. ABC means there's a cluster that contains A, B, and C. So pictorially in the fan, it looks like that. They don't have to be connected by edges. Also, they will have to. Well, so that's still under investigation actually. But you can have a situation where there's a simplex like that. A, B, and C are in the same cluster. So that's the picture to keep in mind. Or they're AXA prime, meaning A mutates to A prime. So mutation pairs cannot appear next to each other. So I need to separate them by one. And that's what's in the middle is unique. So when I present symbols, in other words, I don't need to put what's between two mutation pairs. That is the x coordinate that corresponds to this mutation, always. Pictorially, you have a cluster like that, and you have one point here is a G vector corresponding to that, and that mutates to here. And there's a, well, X variable corresponding to its face or mutation, and the triple you get is AXA prime from there. And this is not restricted to cluster algebras, by the way, so I'll mention that.
For example, the triples in the H2GGG kinematics that Yorgos mentioned. Okay, so yes, maybe there's the C2 case or the sub A3 case, whatever you want to call that. The alphabet has 3 letters, U, V, and W. 1 minus U, 1 minus U, 1 minus W, under the constraint that they all sum to 1. Equivalent alphabet is just, you can take your ratios or products of these. ABC, the standard ABC ratios that are used in hexagon, U over V, W, and rotations. And D, E, F are 1 minus U over U, etc. Right. And for these objects, the pair conditions are A cannot appear next to D, and cyclic, and D cannot appear next to E, and cyclic. So this cannot appear, this, that, and there are also 3 other types of 3 of the other type of geometries. And now you look between A and D. Only B and C appears between A and D. So this type of non-adjacency only has B and C in between. And between D and E, you only have C. And that's true for all integrable words, these adjacency conditions. Mind you, the actual object, the amplitude, has 3 more triple conditions. I'm not talking about them. So these are not all the triple conditions, but they are very much cluster-like triple conditions. And when I look for cluster adjacencies, investigate these triples. So what appears between the 2 things? It gives more clues because you might be in a different wrong basis, unsuitable basis for adjacencies. But yeah, how many independent things appear between 2 things is an invariant state. Okay. Now, as I said, I need to take a linear route. So I'm jumping back a bit and talking about bootstrap beyond MHV. I'm talking about symbol letters, but don't forget, there are Youngian invariants before these polar logarithms, not multiply. And can be seen as the canonical forms of codimension 4L boundaries of the corresponding octahedron, as many of us like to think about these. And so another observation that's been made is that the poles of these Y invariants, like the 5 brackets I showed, are cluster compatible with the final entries of this polylog. So you can think them, actually I've written this in a bad way, I should have written this Y here. These look like the actual final entries, like a new entry in the symbol, and poles of these are cluster compatible with the final entries of the symbols. And important remark here, these Y satisfy identities, are invariant identities. So there's no unique way of writing these. And to make this adjacency manifest, you need to give up integrability, manifest integrability. So you need to use all of the Y invariants and make integrability only satisfied on the Y invariant identities. But then you can make the adjacency of these poles and final entries manifest. So, but that way of writing is not manifest either. And I will comment on this afterwards. So it's not unique either. Okay, and that's the answer lies here. Yet another adjacency story. Again, jumping from topic to topic. Young invariants and Landau singularities. So these letters, flickers, polynomials thereof, or non-rational functions thereof, crop up 2 things in the boundaries of the poles of the volume forms, poles of Youngian invariants, and the singularities of scattering amplitudes. So they're very related things, but they're not the same thing. And if to complete the singularities of the scattering amplitude, there's a machinery of the Landau equations. So you write your integrals, the integrals you need to make. So this stuff
I advocate that you should look at Feynman integrals. Now I'm looking at Feynman integrals, but okay, there we are. So as this form, the numerator and the denominator. And the denominator depends on your parametric integrals as well as the loop integrals, QI. So QIs depend on L by some shifts of the P's. P's are the externals. And you get two types of equations. Cut type equations, where the propagator times this parameter is 0, or there are like Kirchhoff type of equations. So alpha I, QI, summed over loop, the edges in the loop is 0. And in the maximal cut, if you consider the maximal cut, mean these are all 0. So alpha i's can be non-zero, and you solve these equations accordingly. And then these are the lambda equations, and you can solve these for kinematics to find where the integral develops singularities in which kinematical configurations, and these will become the logarithmic singularities, i.e. the symbols, letters that show up in the symbol. Okay, but this may produce spurious singularities cancelled by the numerator, and these colleagues had a way to compare the Landau singularities with the loop amplitude and to find the actual physical ones. So they had the table, and yeah. On the other hand, the leading singularities. Sorry, there was a question? No. Okay, so that was something. Leading singularities, on the other hand, well, the residues of the integrals on a cut configuration for the loop. So there's a solution for the cuts for the loop momenta, and I evaluate the integral, and that's a sum of y invariants. So the cuts of an integral defines the two objects: a leading singularity in that way, or a Landau singularity. So cut tells you which alphas are non-zero, sorry. You get the compute a Landau singularity through the prescription from here. For example, take this 3 mass box. From here, you find a Landau singularity that is quadratic in Pluckers, like that. And a leading singularity corresponds to Scout configuration, which is a 5 bracket, is an R invariant, I, j minus 1, kk plus 1, has 5 poles like that. And now the observation I made with Matteo Parisi is that there is a cluster that contains the Landau singularity, this one, and the poles of the leading singularity all together. So I made a slightly weaker statement earlier that the final entries are pairwise cluster compatible with the poles of the Young invariant. I'm saying that they're all in the same cluster. Okay. And we check this for all one loop amplitudes with multiplicity equal or less than 9, and that's prove this for all NMHU one loop amplitudes. Okay. Remember, I told you that the presentation of the amplitude is ambiguous because of the y Young invariant identities. And now, once this, if you want to insist on that fixes the presentation of the amplitude. So it gives you a canonical way of writing the amplitude. We only check this for 7 points. It's worth something that needs to be checked for higher points at one loop, of course. Okay, so now another topic that revolves around the bootstrap, octagon kinematics.
Sorry, Omer?
Yeah.
About this one loop, has there been more check beyond next geometry level? Like the pole of Young invariance and the last entry?
Yes. Yeah, there's a something with the square roots, but then the data set once you you need to sum over 2 to, well, I just assume that you're going to ask about the square root poles, but is that what you were asking, or is
including that one? I mean, the square root pole is considered part of your. I mean, you also need a square root pole to be adjacent with the last entry of the.
No, but you need to add the two solutions, and then in the total they go away.
I thought the Yangian in front of the 4 mass box is the difference of the two solutions, right? Not the sum.
No,
Am
they are not actual poles of the leading singularity, as far as I remember. Is Matteo here? No. Okay, that's
Okay,
all. They're not
let's
actual poles, so they don't cause a problem. That's not so. Okay.
Okay.
Right. Octagons. So all sorts of things change with octagons because of 4 mass kinematics. So if you have 8 massless legs, you can have 4 massive combinations like that, and the combinations, the cross ratios you can build from them are the 2 particle invariants divided by 3 particle invariant, 4 particle invariants here. 2 particle invariants, 4 particle invariants. So 4 are the cross ratios for the 4 mass box, and you can change that. That will give you non-rational functions of the u and v, but you can rationalize this by a change of variables into z's. But your problem is that your alphabet can either be rational in z bar or in the applicators. So there's a trade-off between the two. So we need to learn how to live with the square roots. Another problem you get is that 4,8 is an infinite cluster algebra, and it's quite well known. I'm not going to go into too much detail. Is that the two problems cancel each other? The infinities obviously give the non-rational letters. So yeah, because finite number of mutations, which are rational transformations, cannot give you something non-rational, but infinite ones do. Right, and how do they do that? So let me briefly review this story. You can find a cluster in the 4,8 that looks like this. So a double arrow here, and 3 a coordinates go from the z on to w, and collectively I denote them p, and some of them go into z of the frozens. Some of the frozens go out from come out from w. So that's a pictorial representation of an origin cluster. Actually, there's 9 nodes, but I only care about this case. And now you can mutate on z, that becomes the w1. You can mutate on the w, that becomes the w2, and carry on like that. And yeah, the mutation sequence is that the n plus 2 w is related to 2 previous ones. It's like a Fibonacci sequence. And you can do this same thing on the other strand. N minus second z is related to the 2 previous ones, same Fibonacci sequence. And you can solve this sequence. And for the n step, for example, for the z's, you'll get this expression. This doesn't look rational, but it is rational. And then you have a problem when n goes to infinity, this diverges. But you can look at these coefficients, and then you see that they are the letters that Solomon collaborators have found for the, well, they span, multiplicatively span the letters that Solomon collaborators have found in the NMHV result, and which I will call phi z and phi w for the 2 strands, and they are related to the, well, they are defined by the values of the z2, w, and these f's in some way that's not relevant now. Okay, the important part is that you get 2 letters per origin cluster of all 64 of them, and there are only 18 independent combinations, and they're exactly the ones that were in the amplitude. So there's nothing superfluous from here, nothing missing either. Exactly 18. So that's great. And I want to clarify the relation of these to the scattering diagrams approach that has been introduced by Aiden Herdership very recently. So I told you these mutation sequences diverge, but there are better variables to consider, which are the y hat gammas instead of the x coordinates of these I've been using a coordinates in the previous slide, but you can also consider x coordinates, but they will diverge too. But you can define these y's that are just multiplicative combination of the x's. You can invert this relation. So the y's taken some powers, multiplied together give you the x, and these powers are related, are found by the normal vector through the wall that you're crossing when you do the notation, and the g vectors there. And so this is how they're related. And now you can compute these y hat gammas, and you find that the limits converge this time. So you can actually honestly take these limits. So this you might say, oh, okay, this is a bit cheating. You see the coefficient and declare this is the letter, but here you can take an honest limit, which is great. And you see you have 5 y hat gammas that are non-rational functions of the kinematics. So these 5, 6, 8 in his notation, I contain this 1 and 9. But the honest non-rational letters are these divided by their conjugates when you substitute square root of delta with minus square root of delta. And so these 3 therefore only give 1 because this rational prefactor cancels. So that thing that is called F in that paper is 1. And there's y hat gamma 1 and 9. And right, so I'm doing this well, there have been questions in other meetings how the two methods are related. I'm doing this to clarify this. So the gamma 1 is exactly the phi double squared. Gamma 9 gives you exactly phi z squared from one origin cluster you get the 2 letters, and then these extras are just the products of the 2. So you only get 2 per origin cluster, which is compatible, and in the end you get 18 independent, only get 18 independent multiplicative combinations, and that's what also observed by Popov and Nasir and Henke recently. Right, so we have non-rational letters, we have non-simplicial situations in 4,8, and how do we infer adjacencies from that? So that's an open problem. I'm not going to answer that, but I would, as I'm running out of time, I would like to give you some clues on how I'm thinking about this and tell you how I'm thinking about this. So some more astronomy. Song and collaborators, 2019, computed 2-loop NMH octagon. And when I was preparing this talk, I wasn't aware of their results that came out this morning. So I will be talking about this. But I think the story is very similar here. All non-rational letters appear in this form here. So this I wrote a weight for quantity. The first 2 weights are here as a Bloch-Wigner dialog. So U and V's are the initial entries, and second entries are 1 minus Z's and Z's, like that. And the phi letters appear only in the 3rd slot, and there are some final entries multiplied by some Young invariants. So that's the form we're looking at. And if you wanted to bootstrap this, you will want to know what these appear next to. So that's the question here. And these are, as I said, multiplicative combinations of these phi double and phi z's, and there's 128 of them for the 18. There's many ways of writing these. Which is the right way to write? This is one of the problems. How do I write this correctly? So I don't know that. And these ones, the final entries, are rational. So so is there a correlation between these and these? That is the question. Okay. Now, when you look at what appears here between a given dialog and here, there's a unique combination that appears. So it sounds like there's no information here because I fixed this and I fixed this and I look between, of course, unique things appear, but across the Y invariant. So these things can appear in different Y invariant or invariant structures, but there's a unique combination. So that smells a lot like the AXA prime that I mentioned. And some of them are like that. So let me clarify that. So I just copied what's the form. So we have these and Fs. These I can think about like the limiting ray. And there's another ray, G vector, corresponding to these rationals. Okay, maybe I haven't emphasized enough. We have 2 limiting rays in 4,8, but we have 18 letters. So that those statements are made. 2 rays connected with an edge are adjacent to each other are not applicable for those. So the reason I'm talking about this is we need to find a way of articulating. We need to find a rule for this. And where is the 18 in the polytope? Well, there are the origin clusters in the polytope, not as cones, but there are cones that contain the origin clusters that give us 2 letters. And okay, one observation, relevant, I don't know, that these can be written as quadratic combinations of the phi w and phi z. So if you wanted to, in general, if you wanted to write them as in terms of phi doubles and phi z, you will need to use many factors, but you only need up to 2. So, but once you've written them in terms of phi z and phi w's, now you are in the geometry. Now you are looking at some certain clusters, cones that are associated with these phi's. Okay, and then you can ask, are these related to the limiting rays? And well, almost. So okay, so that's the second point I made. So the phi w and phi z define an origin cluster, and these are inside a non-symmetrical cone. And you find that either these phi's are connected to a limiting ray. So that's the way we so this tree is like an ABC, or there's the AXA prime situation, or there is a say this is the limiting ray. Of course, this is not a simplex, so maybe I should have added another node like that. But the there is a cone always. I mean, if that's not the case, if they're connected, there's always a cone that contains the Fi and shares a face with the cone that contains limiting ray. It's like the mutation case. They look like the mutation case. Unfortunately, I can't say anything more. But yeah, so it would be great to understand these in terms of AXA prime language. Okay, so I'm coming to the end. Let me summarize. You can either try to understand and love Feynman integrals or try to avoid them. And the bootstrap method is trying to avoid them, Positive geometries are full of clues on how to do the latter. The rules of the main thing I want to emphasize was that the rules of the game are still unclear. There's a lot to learn, and hopefully we'll get that to space that contains only physical things. And I think there's lots to learn from triples as much as there's from pairs. That's all. Thank you very much for your patience, and yeah, forward to your questions.
Thank you. Questions?
Oh, maybe I should not share it.
Omer, I had a sort of a qualitative comment that when you when you talk about the sort of Yangian invariance out in front of the symbol, it might be worth thinking about the Yangian invariance out front, as we know in this sort of bosonized way of thinking about super amplitudes, that the Yangian invariant out front is itself a 4K D-log form. So of course you can write it as the sort of final answer, where you just see a bunch of poles and so on. But it might be, I mean, it looks formally interesting that the way those Yangian invariants come out of the box is really 4K D logs, right? It's 4K D logs of ratios of brackets.
So you want
And
to write the
then-
symbol of them.
Yeah, I mean, so there's some kind of big combined symbol where there's D log, D log, D log, where the things inside the D logs are, just ratios of 4 brackets, but are not little group invariant. They're just ratios of 4 brackets, they're not little group invariant.
Yeah.
And then you have the symbol part with tensor, 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 where all the stuff inside is little group invariant.
Apart from, it needs to be commutative, I believe.
Sorry?
Order shouldn't matter, I believe.
For yeah, well, on the, up to the sign, of course, yeah, up
To the side, yeah.
up to the side, yes, yeah. Yeah, and I think that we've probably also discussed this off and on with you and other people, and actually, I guess it came up in last week as well, that one might be able to make the connection even closer if we sort of take out the torus from the z's on the side of the D logs. So if we somehow take out the little group scaling, then as sort of part of the story that we were talking about last week, relating the momentum amplitude to the icosahedron, there, if you sort of take out, if you write z equals t times some z hat, then the 4K form turns into some it has at least one term, which is a D log of a bunch of these t's, then multiplied by something that's only D logs of cross ratios now. So then it's even more similar. Anyway, that's just a comment that it looks at least amusing that when we bosonize everything, and it's important to bosonize in order to be able to do this, because if we leave it in terms of the super amplitude, we only see a sort of a big object over a bunch of poles. And even the number of poles might change from term to term and so on. Whereas when you bosonize it, it's always 4K D logs. And yeah, so somehow that seems more closely related, that the objects in front and the objects in the symbol are more closely related to each other.
Yeah, there might be something to write this like whole one big symbol. Yeah, thank you for that comment. We're still talking to Matteo about this to go further with that. So yeah, should consider that. Thanks.
For questions? I have a general question. So is there anything observed beyond this triplet?
Of course, the initial and final multiples saturate with loop order, so that's one thing. But I don't know anything that I can say concretely apart from triples. No. Sorry.
Okay.
Yeah.
And Omer, can you maybe summarize? Let's say it's 6 points, as simple as possible. What ingredients go in the end that sort of uniquely fix the symbol so far? Like
6 points is worse. You said it's simplest, but it's not.
Oh, sorry, yeah, but you're right. But let's do 7. You're right. Yeah, seven at least has this thing that it should go down. Yeah. So whichever one you want. Is there any? Is there a sort of a minimal set of rules that you can say it's integrable, first entry, last, whatever? Yeah.
Yeah,
say whatever you want to say about it. Yeah.
For everybody, maybe I should say why it's easier, because in 6 points you need some dynamical information from the OP, but 7 seems to be more constrained, and you need integrability and adjacency, and dihedral symmetry, and a sensible collinear limit. Sensible
collinear limit means that it should reduce down to 6 point.
Not even
or vanish. Yes.
No, finite. It's being finite.
Oh, finite. Just finite. I see.
You don't even know what it is, so it's easier to get the 6 point amplitude from 7 amplitude.
I see. And that's it.
That fixes it. Yeah, up to 4 loops, right?
And so you don't have to say anything about triples or anything. All of this comes out.
Triples come out, yes. But just I advocated triples only to be able to make statements for the octagon letters, but
Right.
you don't need that.
Right.
No.
Right.
No.
And
Sorry, do you still need first and last entry?
Oh, of
Sorry.
course. Sorry, I designed.
First and last entries are
Sorry, that
implied.
was. I thought that was given.
That was
So,
part
yeah.
of the
Yeah.
All right.
First and
So-
last, of course. Yeah.
first and last entry, just repeating, first and last entry, integrability, adjacency, and finite collinear limits,
And dihedral symmetry.
and dihedral symmetry. Right.
Yeah.
Okay.
Sure.
That's all you need. It'd be great to bring other computations to that level, but you need more information, of course. We know many alphabets, but we can't. It's not that simple.
And can you just even qualitatively say which one of these things is the biggest cut on the size of the space? I mean, just even roughly.
Well, that depends on what weight you're considering, but asymptotically, the triple okay, and what problem you're looking at? We have
7 point. I mean, even the
7
example
point
you're just talking about.
adjacency is changing your asymptotic behavior.
I see.
And for the form factor kinematics, triples, but including the 3 ones that are not implied by the adjacency, they make the biggest damage. And the knowing the initial and final multiples.
I can maybe add a comment here. I agree with what Omer said, but I think a large part of the power that we observe in at least the amplitude bootstrap is that the collinear limits, those constraints, just strict collinear limits, seem to be almost totally orthogonal to these Steinman or cluster adjacency constraints. So you get a lot of power out of the combination of the two. We just in practice tend to implement the adjacency constraints first. So we see a lot of that power first, but somehow these two constraints together are way more powerful than each individually.
Actually, yes, because you can't impose collinear limits from the get-go, but you can start building symbols that have adjacency. So that's why we do that. Yes, right, actually. Yeah.
Hi, Omer.
Hi.
So only to understand if I understood it right. So in this n equals 7 case, all these constraint give you words that all the words that you get appear in the amplitude. You don't get anything extra.
All the words appear in the amplitude. You don't get an.
So like how big is the space respect to the one that you in the end need to represent the amplitude? Do you get like extra stuff or?
So I don't know so much to things you are comparing. So you mean everything that's allowed appears in the amplitude? Is that the question?
Yeah, I mean,
no, but that's
sorry, I don't know if I understood it correctly, but you have all this constraint that you have your symbols, and now you want to have constraint on the word, like adjacency,
yeah.
Right? So you start with a big space of words, and then you are reducing it, and then I guess you can look at the answer and see what are actually the words that appear in the amplitude, right? And you can see if your space is bigger than that, or is exactly just the thing that appears, right?
In some cases, you nail down exactly. So heptagon cases, there's nothing else in space left after the constraints I mentioned. But for in some cases, there's some junk, and you need to use some dynamical data like the OP or neo-collinear limits expansion of the object.
Okay.
To be able to nail that.
Sorry, Omer, but in some sense, the last entry condition still contains some dynamics in it, right? I mean, it's not like something you immediately see in even first. I mean, first entry, but it's easier to understand. But both first and last entries are not something cluster algebra can tell you, I would say. And then collinear, but these are of course not as dynamical as OPE kind of thing, of course. Yeah, these are much more set. Yeah.
I guess I distinguish dynamical and non-dynamical as in it's not dynamical if you can say, if it's just like a grammar rule. Yeah.
Okay. Yeah, that's fair.
I use this first in that sense, but I agree it's a bit ambiguous the way I use the word. Yeah.
Like just again a curiosity, but when I'm thinking about this condition. And then I'm thinking that the words like scale with L, right, becomes bigger and bigger. And all these constraints are kind of local, right? Like adjacency or the triplets. Do you think there could be some like more global condition on the word, like something that maybe doesn't have to do with the order, but just what letters appear?
Yeah, what letters appear is all conjectural, and at the moment we believe, for example, for the 7 points that or 6 points, that is the alphabet, and that's it.
Yeah, but I mean in a word, like I don't know, I can't have like a 6 times the same letter or something, some condition like that. That you know doesn't depend on the length of the word.
That there are ELF discontinuity conditions that I haven't mentioned. For example, there are similar things in that spirit, so that ELF discontinuity increases with loop order. Yeah, and in the form factors, you see that, or in apt sketching up, as you see, there's a saturation of the initial multiples, but don't think I know anything exactly of the sort that you're after. But there are similar things that I mentioned.
Although maybe you could maybe one answer to your question is integrability mixes different words up together. So that's at least some. So so indeed you're right that these guys have they're giving constraints on the letters that can occur in a given word, but integrability really mixes them all up together in an important way to put a global constraint on things.
Thank you.